Hey guys, in today's video we're going to look at congruent triangles and we're going to review the ways of yeses and nos. Can we guarantee that these triangles are congruent or not? And we're going to try to find information to prove they're congruent within pictures. So let's get started. So in this diagram, there's actually already a special pair of angles that we know. If I mark it for you, can you tell me what these angles are called? Cool, these are vertical angles. And what do we know about vertical angles? Yeah, vertical angles are always going to be congruent. So now they're marked in the picture as congruent. Okay, so let's think about ways that we might know that these two separate triangles could be congruent. I know that side, side, side would make them congruent, side, angle, side, angle, side, angle, 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 side, or hypotenuse, leg. Those would be my options for guaranteeing that these are congruent. Which one of these do you see in the picture marked now? I'm going to go over this one. So this is the postulate that guarantees that these are congruent. We've got a congruent side, a congruent angle, and a congruent side in that order. And therefore, these two triangles are congruent by side, angle, side. And just pay attention to how you're naming those triangles so that you're going around in the same order. A would correspond with E because those are the angles that are attached to the side length that is only marked once. Here's A, and here's E with the side length marked once. Then they went to the opposite corner, so A, B. B is up here next to the side that's marked twice. D is down here next to the side that's marked twice. And finally, you'll notice both of the triangle names end with angle C, which we know corresponds because those are our congruent vertical angles. What about this diagram? You should notice the same pair of angles in the middle of the two triangles where they connect at point K. What are those called again? Sweet. And so since vertical angles are always congruent, we can now try to find the criteria, or the theorem in this case, that proves that these are congruent. You'll notice that we have a side marked congruent again, followed by your vertical angles that are congruent and another pair that was already marked congruent for us. Therefore, these triangles are congruent by, we usually call this angle, angle, side. And again, just pay attention to how you name the triangles, making sure all of your angles correspond in the titles of the triangles. Alright, here's a picture of an isosceles triangle. You guys know that isosceles triangles have two side lengths that are congruent. All isosceles triangles also have base angles that are congruent. This is a theorem that we haven't had a chance to prove, but it's already marked in the diagram for you. So right now this is only one triangle, so I'm not asking if we have any congruent triangles yet, but what if we were to add a line that goes from the midpoint of ZY to the vertex across from it, which is point X? There's the line I'm talking about. We've now made two triangles. So you've got a yellow and a blue triangle that are now two separate triangles that we could ask, are the yellow and the blue triangles congruent, and how would we know? Well, we don't quite have enough information yet. We have a side and an angle marked, and we don't want to make any other assumptions, so be careful. Like for example, point M down there, they sure do look like 90-degree angles, but I don't want to assume anything about that because we weren't told, and we don't have a theorem yet where we know that for sure. So instead, let's focus on the fact that we just made this by using a midpoint of the bottom side of the triangle. So what is a midpoint? If you start with the line segment on the bottom of the triangle, which was ZY, you know that a midpoint is going to be exactly in the middle of Z and Y. And so what it does is it creates two congruent pieces of a line segment. So check out the base of the triangle now. We can mark ZM down there is congruent to MY. And so now in our two separate triangles, we do have enough information to guarantee that they're congruent. What would that criteria be? Okay, awesome. And again, naming the triangles, both of these we started up at vertex X, and then we went to the outside to those base angles, Z or Y, and then we ended in the midpoint, M. And they are congruent by side angle side. Okay, this diagram looks very similar, but we want to be really careful in math that we do not assume anything that they haven't told us. This is not necessarily an isosceles triangle, although it does look a lot like the picture that we just had. Since we don't want to assume, we're not going to look at those base angles, we're not going to make any assumptions about maybe a possible right angle and this being HL or anything like that. We just want to go with something that we know guaranteed 100% for sure. So let's look at these two separate triangles, the green and the purple. What I'm noticing is that they have a shared side. So both of these triangles share the side AD. Well, this might seem really obvious, but AD is congruent to itself, and there's a property in math that says that. The reflexive property says that any object is congruent to itself, so AD is congruent to itself. Now what criteria do you see marked on all three pieces of the triangle? Okay, all three sides of the triangle are now marked in the green triangle and the purple triangle. And so those triangles are congruent by side, side, side. Alright, so that should make this last one pretty easy. We know that because of this diagram and the way that it's drawn, we can use the reflexive property to assume that BC is congruent to itself. And so that line right in the middle describes that property. And now if we look at the markings on the triangles, we already can guarantee that they're congruent. How would we know that these triangles are congruent? Excellent. Triangle ABC is congruent to triangle DBC by side, side, side.